Alright, so really quick I'm going to recap because the video did not record yesterday. Anything but the first 2 minutes. Alright, so some basic relationship definitions that we made yesterday. Data is also known as a payload. Protocol, that's another word for rule. Logical, to us this should mean software wherever we see it. And so far I think that's all we've done. And the first layer of the OSI model. So the first layer of the OSI model is the physical layer. And what we've been doing is looking at the physical layer, we're looking at the details of what is the OSI model responsible for in each layer. We said the physical layer is responsible for the rules for construction. And that's not what they're called, but they're called RFCs, so I like to say the RFC stands for rules for construction. What really it is, it's a standardization of some technology. This one's IP version 4. They have it for twisted pair cables, they have it for routers, switches, and hubs. In the list is a description of what will a hub be, what will a cable be, what will a connector be. So for the RJ45 connector would be a rule here that says, you know, it's got the little lock so it clicks in and locks. It's got the 8 pins on it so that it plugs in, the size of it, the shape of it. For every device and pieces of hardware, RFCs come at the physical layer. We call this electrical and mechanical specifications. So that's one rule that's set down at the physical layer. Now this doesn't mean that this hardware functions at that layer. It just means that the rules for the development and standardization of these are at the physical layer. In the old days, you would buy IBM products. All your products had to be IBM. The cables only fit with IBM NIC cards. If you had any Dell products, they wouldn't fit together at all. This is called proprietary hardware or software, if it's software. Proprietary just means that it's company specific. So they got away from proprietary parts and they came out with what we call standardized parts, so that the RJ45 connectors fits every NIC card. The hole in the NIC card is the same. The card fits into a motherboard exactly the same. You could buy 10 different brands of NIC card, it's going to fit into that PCI slot. The PCI slot is the shape that it is because they set down a standard and rule for it. We have IP addressing because they set a rule for it, so IP addressing in China is the same IP addressing that we have here. So everything works the same. That's a rule that they set down at the physical layer. Now, what the layer is responsible for is not the same for what items function at this layer. So there are also some rules at each layer for hardware, and the way that we know that hardware functions at a particular layer is what is the addressing that this layer has, and that would be the addressing that that particular hardware is concerned with.
Plus hardware is physical. So.
That's true, but see, that would be in the first part. The first part where I said there are rules for specifications. That's the only time that we say something's at physical, because I can touch it. That's true, but it doesn't function at that layer. So everything that you can touch is at the physical layer, not because it functions there, but because the rules for that product have been set down at the physical layer, specifications for it. But we're moving on away from that into how do we know what hardware functions at a certain layer. And we know that hardware functions at a certain layer when we look at the addressing that that hardware looks at, and we look at what does data look like at that layer, or what's been added to data to create the protocol data unit. And what that means is, what does data look like at this layer? So the rules for the units of data at each layer. And so what we said is that the addressing at the physical layer is, there is none. But it makes us ask the question, how does data get from one place to another? And the answer to that is broadcasting. So just like a television, it shoots the signal out to everyone. All the computers have access to that data that's coming in, but they won't process it unless it contains the MAC address included in that information from the NIC card that it's receiving. So it'll look at the MAC address and go, that's not my MAC address, and it'll ignore it. One computer will say, that's my MAC address, and it will process that information. So once we get past physical layer devices, other devices look at addressing. So the NIC card must probably have something to do with MAC addresses, and we just haven't got there yet. So so we would know that there's no addressing, and broadcasting is how things get around at the physical layer. So our question would be, what hardware broadcasts? And before we answer that, what does data look like at this layer? Devices at this layer are only concerned with bits. That means a 1 or a 0 in the form of electricity on a wire. This is called binary transmission. It comes into the device, and then it just propagates that 1 or that 0 out back onto the wire. So it only looks at the bits, it doesn't look at anything else. No addressing, none of the data, it doesn't care. The two devices that function by only propagating bits or broadcasting are a hub, most often found in a local area network, and it is a 1-in, many-out device. It provides multiple connections to computers for a network. Of course, I just said that backwards, but it provides multiple computers a network connection. Same thing. Today, we don't use a lot of hubs, and it's because they broadcast. When you have a lot of broadcasting devices on a network, that means you might end up with a lot of what? Too much data going in many directions on a cable. What might happen?
Oh, corrupt data.
Because it collisions. Your data may become corrupt because of collisions. But see, there's another issue. It's not just collisions, but a broadcast storm may occur, which isn't corrupt data. It's just a cable so filled with data, the bandwidth has been all used up, and there's no room for it to go. For instance, if you fill the water hose full of water, and it's going moving around in there and flowing through, you can't take your finger or a spit wad and try to shoot it back up the hose. There's no room because of all the water that's traveling through it. So the bandwidth of your network cable is all used up. Now on the WAN side, we have another device that broadcasts or is only concerned with bits, propagates electricity out on a wire, and that is the repeater. It's found in the wide area network. We used to say at the tops of telephone poles, but nowadays they bury them. Repeaters, of course, can work with copper cable or fiber optic, and their job, they're a 1-in, 1-out device. They regenerate signals, they clean up signals, and this is to defeat attenuation, because electricity traveling down a wire loses strength, just like water going down a hose. There's a friction that occurs between the electricity and the copper cable. So in order to extend cable distances, you throw in a repeater. So every 1,000, 2,000 meters, metric kilometer, when it moves down this cable and your signal's getting weak and it's getting degraded, you just throw in a repeater so that you can run it another 2,000 feet. Unless you need to split it, and then of course you would use a different device. But most of the time, when you just see it going down the street, like say from one city to the next, it's just going to be runs of cables and repeaters of some type. Alright, so in broadcasting, to better understand broadcasting, I broke out the old bus topology. And this is normally some kind of coaxial, a thin net or thick net, your 10 base 5 or 10 base 2, there's another way to say it. This cable specification is kind of like the TV cable that you're used to. The connector on the end is a little different. It doesn't have that, for TV it's called an F-type connector. For your internet card, it's called a B and C connector or a barrel connector. It just has a little lock, it's a little pin that sticks up, and you put it in, you twist it, and it just locks into place. So here I've got 5 computers on a bus, and we have some caps on the end of his, and these are called terminators. Termination of a bus cable means that when information gets put out on the wire, when that information hits the end of the cable, it's stopped. It doesn't bounce up and down the cable, because then we can get a broadcast storm or a bunch of collisions. Alright, so basically how this works is I got computer A, B, C, D, and E. If computer A needed to send information to computer D, computer A would then put out the data on the wire. It would travel down one side, hit the terminator, and stop. But it would also travel down the other side, and B and C would hear this information, but they would ignore it because it's not my MAC address. And D would hear it and go, that's my MAC address, and it would process that information. but E would hear it not paying attention, and it would also hit this terminator down here so it didn't bounce back up the wire. So this is simple broadcasting by nodes on a bus network. This is coaxial, and I said these computers basically are about up to 18 inches apart. There's a little mark on the cable that lets you know where to take that T connector and screw it in so that the vampire taps stab into that cable. And that's about it for the physical layer. So on a quiz or a test that asks, name one piece of hardware, the one PDU, and addressing at the physical layer, you should have none or broadcasting. That's one type of addressing. You should have bits, electricity on the wire, or binary transmission. One of those is a PDU. And then a hardware, I need hub or repeater. If you have hub, repeater, and none, you have a wrong answer because you're not telling me a PDU. So remember, the question is one piece of hardware, one example of PDU, and one type of addressing that occurs at that layer. Alright, so we went over this yesterday, so you should be good on most of these notes, right? Alright. Alright, so today what we're going to do is talk about the data link layer. Alright, so the data link layer is divided up into two main parts. Do you remember what those parts are? What are they?
Parts.
Two main parts that the data link layer is divided into.
The MAC layer
Yep.
and the sub layer.
Almost. The MAC and the LLC. Now what do those stand for?
MAC for addressing.
Well, what's it stand for? You gotta listen to the question. Means what do those letters mean?
Media access. Computer.
Control.
Yeah, control.
And the LLC. This is where we're getting that word we need to look at, logic.
Link.
Logic link control. Now I know you've seen this before, because I saw it on Mr. Stiller's board when I went in there. Alright, so we know what control means, right? And we know what access means, right? And we know what link means, because we use these words pretty much every day, right? Oh, let's look over there. We got a word that we can replace. Do you use logic every day?
Yeah.
As a word in a sentence, I hope you do use logic every day.
Yeah.
But as a word in a sentence, you don't use logic every day as a word in a sentence, especially when it comes to computers. So over here, we already said that we knew a word we could replace that with. So logic means what?
Software.
That's right, software.
Software link control.
That's right, but remember I told you yesterday was a trick to understanding this stuff, so let's worry about filling in the word first, and then we'll see what it means. Alright, so media. What does media mean? Aha. So let me tell you a little story.
Multi-ethnic destruction and
Not that media. But yeah, you're close to right about that one. But in this term, media, oh, you want to talk today, huh? You must not like your little lecture yesterday. So, media, you can remember that, but you can't remember.
Oh, it's on the computer one.
Alright, media. Okay, I used to go to a store called Media Play. And Media Play sold CDs and DVDs. So, you know, they had movies and music, but they had magazines, newspaper style and the paper style. They had, back then, they had records probably even then, you know, because kind of that. But I also hear that, like, information comes to you through the media, and that's newspapers and news shows, you know, CNN and MSNBC and all that. But what does media really mean then? So I kind of figured out that what these things had in common, what they were sharing information, right? Even if it's music or a movie, in a way, it's still sharing information. It's sharing dialogue, or it's sharing, you know, whatever the new songs are about. Some of them could be politically, some of them could just be party. But the message, there's a message of some nature, right? So it's kind of sharing information. But then I was like, so does it mean sharing information? But I was like, but that's CDs and newspapers, and then the news television. That's what really set it off when I said, well, they're sharing information, but I don't get anything solid. So what media must mean is what you're using to share the information, which is medium. And then I remembered that from art, because they would say, well, what medium do you work in? And they'd say like pen and ink or pastels. So it kind of clicked in my head that media is really a question of how am I sharing this information? So in computer networking, how are we usually sharing information? Now there's two right answers, but you know which one we're looking for, because this is, how does information get from one place to another literally in a computer network?
Oh, the wire.
Yeah, wire, or what's our word here in technology?
Cable.
That's right. Cable. It's the cable. Now, that's not 100% true, because what's another technology we use in networking that doesn't have cables?
Oh, wireless.
Wireless. So in that case, the media is actually the air. But it still stands. The important part is the fact that information is being transferred through the cable or through the air. And we have an analogy for how information travels through the air. We just don't want to talk about that right now, because let's talk about cables. The air is a little simplified. It's kind of like a bus topology and broadcasting and all of that. But we'll talk about that later. There's a whole chapter on that. We'll just stick with cables right now. And so you should know a trick. This is after your media explanation, you should know this trick. Those people in charge, they have a secret, and one of their secrets that they like to use is they like to give you information backwards. And you wouldn't think that this carries over into the education world, but it does.
You were saying one part true, but the other.
Yeah, it'll be one little piece of truth, but a whole bunch of lies. But another trick is the opposites.
You talking about?
No, I'm talking about literally the schoolwork. I'm not getting into that yet. We got schoolwork to knock out first. But what they do is they give you information backwards. So if we read this backwards, let's find out what it's really doing. And another thing that we know that they do, and like for instance, what are the initials for United States of America?
Oh, USA.
Where's the O?
United States of America.
Right, so they left out of, right? Okay, so we might do the same thing. We might need to stick in of or the.
Media
we might need to stick in with.
Media access of control.
Right, but what are we trying to do?
Let's break it down.
Control access to the cable. How do we control access to the cable? With the MAC address. So they're telling you, I didn't understand media access control. That sounds complicated. It sounds like stereo instructions. But when I replaced media with cable, and then I read it backwards, and I said I'm trying to control access to the cable, then I understood what a MAC address was for. Remember that broadcasting data? And computer A sent information, and computer D's MAC address was on that information, but computer B and C and E just ignored it. Because in order to get access to the cable, it had to be my MAC address. So, media access control is the delivery mechanism. So we're going to say that the addressing is right, so what is a MAC address?
An address.
Good one. All right, so what kind of numbering system do they use to make a MAC address?
Oh, binary.
Nope.
No, not right. Hexadecimal.
That's right. The hexadecimal address. And this is just an order of numbers. The hex means 6, decimal means 10, so it's a 16-base numbering system. And so it kind of looks like this. And again, you know, whenever I have numbers and I don't have any specific numbers, I just use X. So this is what a MAC address would look like. All right, so what we also know is,
Oh, and those are encrypted.
no, they're not encrypted, not yet. No, because of the X's. No, I'm using X because I don't really have a MAC address to use. I'm putting X because I didn't want to make up a MAC address. We could have typed in ipconfig right here on the computer, and we could have seen a MAC address, and then I could have wrote one up there. But these here will be anything between 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A is 10, B is 11, C is 12, D, E, and F up to 15. So what you're looking at here is one letter represents half a byte, or 4 binary digits. So 2 of these together is 8, right? So that's an octet. So whereas an IP address is 32-bit addressing, this is 8, 16, 32. So if you add them up, you find out that we have some nice, it's 8 times 6, 48, right, 48-bit addressing. So it's hexadecimal, it's 48-bit, meaning there are 48 ones and zeros, and if you add all of these together, I don't even know if that was English. We should go take an English class real quick. All right, so there's another thing that we should know about them, and that is, how did we get this? Well, the first half here is a network ID. So it's an identification number for the network. The second half right here big boo-boo. Big mistake. The first half is the manufacturer's ID. I moved ahead. I had ID version 6 on the brain. The manufacturer's ID is the first half, so that's my mistake. And a second half is the product ID. The two of these together give us a unique number. That's definitely a number that we want. That's definitely a word we want to remember because they use that on a certification test. They want you to know that it's a unique number. So what is the MAC address? Let's find a color. Well, this is good. A unique address.
Yeah.
And where's it located?
In burn.
Where is it located?
In the chip. Oh, burn into the chip.
On where?
On the back address.
What? Can a MAC address burn into a MAC address?
Back address, but
Where is it burned into?
on a NIC card.
That's right, on a NIC card, on a network interface card. And let's write that out too. On a network interface card. So when we say something interfaces the network, what do we really mean?
On a NIC.
When we say something interfaces the network, What do we mean? We mean that's how it connects. Get comfy. Alright, so let's recap now before we move on too far. The data link layer is divided up into two parts. It is the MAC, or Media Access Control, and what that means is we're going to control access to the cable. How are we controlling access to the cable? Well, we have a unique hexadecimal number burned into a chip on the NIC card. This unique number is a manufacturer's ID, first half, and the product ID, the second half. Alright, so now we have the second half of the data link layer. The second half is the LLC, and of course the same trick is going to work here. First I replaced logic.
What software?
We said logic was software, and that's because a computer has hardware, and that's a physical thing, and that's kind of like a brain, and then the logical side is kind of like a thoughts, and thoughts for a computer is
It's software.
software. So that's how we came up with software, is probably the word that we want to exchange. So we're going to control access to the cable with the MAC address, but then we're going to control the link, which means the connection between two computers, with software. So what this really means is we have a number burned into a chip on a NIC card, but how do I share that from one device to the next? Well, there happens to be a little piece of software that lets us do that, and it's called the Logic Link Control. We are just using software to put our MAC address into it. And this is what we're going to detail out here in just a second when we follow the life of one piece of data or a payload of a particular delivery that needs to be made between two computers. I'm trying not to use words that you haven't learned yet, so it's kind of hard to do. Alright, so let's do that now. Alright, so yesterday we said that you might go on a vacation and take some pictures, and you took a picture that you really wanted me to see, so you decided to email it to me.
Or breaking it down to pieces.
Right, or we're chatting and you decide to send it to you. So the first thing that's going to happen is this thing's going to get broke down into pieces. So here's a picture of something or some kind of data, and then we're just going to break this up into pieces. Now, this don't look like a million pieces, but that's basically what happens. It breaks it up into millions of pieces. And to help it be easier to understand, what I'm going to do is say, maybe my pictures have only been broken up into 700 pieces. That sounds manageable. So we're going to take this one piece, and here it is. So there's my one piece, and I named it data, because that's what it's going to be, all these little pieces. And I'll put it right here. So there's my little piece of data. Now what's going to happen, what happens when, instead of me telling you, let me ask you, what happens when we take a piece of data and delivery information gets added to it? What do we say it's called when data travels through the 7 layers and has delivery information added to it? What was that word?
Is that when data?
When data travels through the OSI model and has information added to it.
Oh, it's
Not peer communication, but the other one.
Encapsulation.
Encapsulation, that's right. So what we need to do is encapsulate. And now on a computer, what it looks like really is kind of like Morse code. It comes in, it comes in a piece at a time in a line. But what I'm going to do is draw it as a picture, because we're going to use a postal analogy to help us understand how information moves. So here it kind of looks like that I've put this into an envelope. So it kind of helps with encapsulation. They're similar in the way they're named, so our brains will stick it. Alright, so I put my payload, or the thing I want to mail, inside the envelope. What would I do next to an envelope if I was going to send some mail? Want me to give you an envelope? Put some mail in it. What would you do next?
Oh, email it.
A real envelope.
Oh.
I know you're young, and you probably ain't ever touched a mailbox. Got a mailbox at home? You ever mailed a letter? So when you take a piece of paper and put it in an envelope, and you close it, what you need to put on the outside of the envelope so you can mail it?
Oh, address.
Addresses, that's right. So at this particular layer, the data link layer, what kind of addressing does it use?
Oh, MAC address.
That's right. So we need to know where it came from. Isn't that how you make out a letter? You put your information right here, right? So that's going to be the source. I don't like that color. I don't know if the camera's picking that up. Let's go back to this dark blue. Alright, so we got the source MAC address. What other address goes on a letter? That's who it came from. Where else is on there?
Oh yeah, your state and
Going to.
zip code and
That's right. That's our source MAC address. But also, who am I mailing it to?
oh your name.
Who am I mailing it to? Destination.
Oh.
You're overthinking. Alright, so we got a source MAC address, and we have a destination MAC address. Alright, so we got a source MAC address and a destination MAC address. And what we also have is some, according to our OSI model sheet that I gave you on Monday, what we have here is some error notification. So let's talk about the two types of error notification that are here, or the two types of error checking that allows you to get notified that there's an error. The first one is not so much an error checking for specific information. It's to make sure that you've gotten the whole puzzle. This has basically become a puzzle. We've broken up into millions of pieces and we need to put back together. Can you think of something that we would do to a puzzle? What we might put on every piece of that puzzle on the back to help us put the puzzle back together really fast?
Oh, numbered.
Yeah, we could number the pieces of the puzzle. And that's exactly what this is. So the numbering of pieces of the puzzle has a name. It's called a frame check sequence. So frame check sequence. On any test, the first time you go to describe or answer with an acronym, you need to write it out. So I need to see frame check sequence. After the first test, you can write what we all commonly refer to as FCS. Once I know you know that it's frame check sequence, then I'll be good with you using FCS from then on. Alright, and then our last piece on our new what does data look like at this layer, that's what we're building, is so now I know how to put the puzzle back together for each individual piece. How do I know that the piece that I get is correct. It's not missing or have extra data or something. Well, basically what happens is a mathematical formula, and the sending computer talks to the receiving computer, and they agree on a number, a control number. So this mathematical formula, this isn't the actual formula, but it's to help us understand what's going on. Basically what it does is data, it takes data. So let's say I'm going to send you 512K of something, and me and you agree on a number, and the number that we agree on, right there, so N, that's going to be the number, and we'll say that our number that we agree on is 4, and what's going to happen is it'll give us an answer. So data divided by a number that we agree on gives us an answer. So what happens is I decided to send you some data. Me and you used our flow control, which we're going to talk about at the transport layer, and data segmentation into maximum transmission unit. We're going to say our maximum transmission unit is 512K, and the number that we agreed on is 4, and that answer is 128. Now, I send this data to you. When you get the data on the other end, let's say that you receive 514K. The number that we agreed on is 4. The answer comes out to 128.25. Is this correct?
No.
No. So my computer would then say I need to request retransmission. Request retransmission. Send me that again, please. It was had extra stuff in it. It's not right. There's an arm sticking out of somebody's ear. Now, just like that one was corrupt because there was extra data, which means, you know, anything could have passed by a microwave oven and gotten a little extra charge and turned one of them zeros to a 1 or anything like that. There's also, it could have come in at, say, 510K, and our number that we agreed on was 4, and it would come out to 127.25. And is this correct? No, it's not. We hear the rocks rattling when he shook his head no. And so basically, we have 127.25, and that's not correct. It's 128 is what we're looking for, meaning there's data missing. Again, data is corrupt, and so if data is corrupt either by having extra data or data is missing, we need to request retransmission. Now this little mathematical formula that I wrote up here, like I said, that's not the actual formula, but that is the basis for how it works. We have data, we agree on a number, we divide it, we get an answer. This is called the cyclic redundancy check. And again, on a test, the first time you use this, please write out cyclic, C-Y-C-L-I-C, redundancy check. After that, you can shorten it to CRC. The verbal C. And now for a commercial. Pepsi, drink it. He was writing notes. Alright, so what we have is data. And what was our nickname for data?
Oh, payload.
That's right, payload. So let's not forget that. Payload. So, let me ask you a quiz question. Quiz question is, what is the definition of, and all this stuff right here together is called a frame. So the PDU at the data link layer is a, say with me,
PE.
the PDU at the data link layer is a
Frame.
frame, that's right. The PDU at the data link layer is a frame. What does data look like at the data link layer?
A frame.
Frame. What is the definition of a frame? Source and destination MAC address. Frame check sequence.
And
Cyclic redundancy check. And
data.
payload. I will accept data. But try to remember payload. It's probably going to be on that certification test that way. So the definition of a frame is the source and destination MAC address, the frame check sequence, and the cyclic redundancy check with payload. That's right. Now the way the book is going to tell you, the book always does it from the direction of a receiving computer. But when they say things about it, they make it sound like it's the sending computer. They say things like, packets get encapsulated into frames at the data link layer. And you're like, well, if I was a sending computer, I'm coming from the application layer. I'm going to go from the application layer to the network layer, then to the data link layer. So in that case, a packet does get encapsulated into a frame and then goes out to the physical layer and gets propagated on to the network. But if I was a receiving computer, then what I would do is tear open a frame to look at a packet. But when we talk about data traveling around on a network, what do we call all data traveling around on a network?
Payload.
Packets.
Oh yeah.
Yeah, packets. So if packets are encapsulated into frames, why don't we call everything frames instead? That always confused me. So try not to let that confuse you. We call everything a packet.
I guess easier.
I think so, but to me it seems like we should be calling everything a frame. If they're encapsulated into it, well, we haven't gotten there yet. I was going to say, does any device inside my network, if one device inside my network talks to another device inside my network, is it going to be concerned with packet information?
No.
No, because we haven't passed through a router. We just went from your computer to a switch to my computer. So now we're going to find out why. And that's because we've talked about the addressing here, MAC address, and we've talked about what's the PDU, that's a frame. So now we're going to talk about the two pieces of hardware that function at the data link layer. One of them, this is a bridge. And we don't use a bridge a lot anymore. If anybody uses a bridge, it's probably because they purchased a wireless bridge and they're probably in a hotel room that offers a Ethernet jack, and what they do is they plug in that wireless bridge so that it can go sit on the bed and play on their laptop or work on their laptop. And they don't want to drag a cable across the room, sticking a 50-foot Ethernet cable in your suitcase just so that you can sit on the bed while you get on the internet with your laptop. And nobody wants to sit at that little desk they give you in the hotel room either. So, all right. So a bridge. How does a bridge function at the data link layer? Well, the first thing we need to know is that all the devices that function at a given layer are able to keep track because they keep a table. And in this case, bridges keep tables. What do you think they keep tables of?
Oh, the topology.
No.
Or the MAC.
They're not that smart yet, but you're on the right track for the future. What they do is they keep a table of MAC addresses. So what I'm going to do is I'm going to draw a picture of how a bridge looks at traffic. Alright, so in order to do that, I need to tell a little story. So first what I'm going to do is draw us up two bus topologies. Alright, so here's our two bus topologies. I've labeled these computers A, B, C, D, E, and F. Now what this is, let's say this is an Eckerd's, and there's a pharmacist, and he's in his upper 60s, and he's decided, man, I'd like to retire. And next door we have a CVS, and a guy who's just finished his school and passed his tests and become licensed has decided, I'm going to open up me a pharmacy, and he opens it up right here. And the guy next door says, you know, I was about to retire. I think I'll sell you my business if you're interested. My inventory is up to date, and we have similar computer networks. And he says, well, that's a pretty good idea. How would we go about connecting our two networks so that I don't have to have new construction built? Maybe we could just put in a door between the two of them, and I make one big pharmacy. And he says, well, my brother-in-law works with computers, let's ask him. So the brother-in-law comes in and says, what you need to do is put in a bridge. So they go ahead and put in this bridge. So I'm going to draw a bridge, and it's basically going to be a box that kind of looks like one of those hubs that we were talking about. And I'm going to draw a cable that goes to each one. It shows it connected to a terminator, but in the real world, the terminators would come off, and they would screw right in to the network interface card connection that would be on that bridge. Now I'm not going to erase any of this, so if you find that you're writing more than you're listening, just wait to draw all that stuff, because I'm not going to erase it till tomorrow. Alright, also it'll be on the video, and you're welcome to, I'm going to put them on that computer. You can watch them anytime you want to watch them. Alright, so here what I'm going to do is show how does a bridge help network traffic, because that's actually going to be a question, not only a certification test, but I asked that question on a test too. And that's just to make sure that we understand how data travels with each device, because those are the questions they try to nail you on. Alright, so we install this bridge and he leaves, and so now we want to figure out how does data travel and what does a bridge do to networking. So let's say computer A wants to talk to computer E. No, excuse me. First, let's say computer A wants to talk to computer C. Let's do local first. Alright, so A, remember our other bus topology, basically what happens is information gets put out on the wire. It hits this terminator over here. Of course, it stops.
And it bounces up.
That's right. Does not bounce up the cable. And then it goes down here to B, and B says, that's not my MAC address.
Puts it back down.
So he ignores it, right?
And it transfers it.
It goes to C, and C says, that's my MAC address. So then he processes it, and you need to remember that because there's a trick question that they'll have on the certification test about routers later, but I'll hit that again. So the information continues down the cable and hits this bridge. The bridge looks at his MAC address table. In his MAC address table, as information passes to the bridge takes that MAC address, and then we'll say computer A, B, C, D, E, F, and that one. And in there, of course, is the MAC address of this computer. The MAC address, and I'm just drawing some squigglies, so I have to write a bunch of MAC addresses. And also in there, it keeps what we call the segment. So this is where people get confused, so I'm going to make sure we focus on this for a second. This is a segment, a physical segment of a computer. It's separated by this bridge. This is another segment. So I'm going to label it segment 1, segment 2. So here in the MAC address table, it would say computer A MAC address is on segment 1. Computer B with this MAC address is on segment 1. Computer C with this MAC address is on segment 1, and then D, E, and F are all on segment 2. You understand that? I will throw a marker. So you see what we mean by segment? It's a section of computers that can hear each other's traffic. That's basically what a physical segment is, and the reason why I don't want you to get confused is in the future there are going to be logical segments. That's why we needed to learn the difference between physical and logical. And we also are going to have ports that are physical and logical in the future. So we need to make sure that we know the difference. At the data link layer, we are talking about physical segments. And in a minute, we're going to talk about physical ports. So, A sent information to C. These guys ignored it because it's not their MAC address. When it hits the bridge checked its MAC address table. It said that computer C is on segment 1, so it does not forward the information. It discards those frames. Remember, we say frames because it functions at the data link layer. Devices that function at the data link layer look at MAC addresses with their information, and they are called frames. Now, the device that on this segment 1 needs to send information to segment 2. What would happen is, we'll say it's E. A would send information out onto the network. It would hit this terminator. It would not travel up and down the cable. B would hear the data. It would not respond because it's not its MAC address. C would hear it. It would not respond because it's not its MAC address. It hits the bridge. The bridge checks its table of MAC addresses and says, computer E, there's your MAC address. You're on segment 2. So the information, the bridge would then forward those frames, and then computer D would hear it and say, that's not my MAC address, and ignore it. Computer E would hear it and say, oh, that is my MAC address. And then he'll process the information. It will still go down to computer F, which will ignore it, and it will hit the terminator, which will then not send information up and down the cable anymore. So, after looking at this, a nice simple way to say, how do bridges increase network bandwidth, would be bridges forward or discard frames based on destination MAC address. Alright, so the bell's about to ring for break, so I'm just going to stop here and I'll pause this up and we'll come back after the break and finish up this square.